Okay, so we are going to be looking at understanding inverses. So inverses is in 5G. So in terms of 5F and 5H, that is extra, but will not be covering that this term. So let's look at inverses. So the main thing I want to speak about an inverse is we have a x and y line right here. Y equals x. Now with this line, it's like a mirror. So when we're talking about inverses, for this to reflect across this line, we are going to switch our x and y values around. So instead of saying 1, 3, I will have 3, 1. So that's what an inverse is. So as they switch, the first thing I want to speak about, our x values are switching. X values normally refer to the domain. So that means the x1 has switched to the y value. So the domain of my function is turning into the range of my inverse. Likewise, the 3, which is the y, has switched with my x value here of 3, which is my x value. So the range, which is y, changes into the inverse of my domain. Now, one key thing that we must understand about an inverse is a function is an inverse only if it is one-to-one. So let's look at some examples here. We've got find the inverse and state the domain and range of the inverse. So inverse will only occur if it's a one-to-one function. This is linear, which means it will always be a one-to-one function. So the first thing we need to do when getting the inverse function is we switch our x and y around. So we're starting off with y equals 4 take away 3x, and we change it to x is equal to 4 take away 3y. The next thing that we need to do is we need to make y the subject. So that means I will take away 4 from both sides to give me negative 3y is equal to x, take away 4. Now I'll get rid of this negative 3 by dividing both sides by negative 3. Now, as x and y switches, our domain of our function turns into our range of our inverse. And likewise, our range of our function turns into the domain of our inverse. So straight away here, we've already been given our domain of our function, where x is equal to or greater than 2, but equal to and less than 6. So that just turns into our range of our inverse. I'm going to use these 2 points and just substitute it into my original function to work out what was the range of this graph. So that means I'm just putting 2 in. The function of 2 will give me 4 take away 3 times 2, and that's 4 take away 6 is negative 2. I will grab the 6 and plug it into my function, and I'll also get negative 14. So now I've got my range here, and my range is negative 14 to negative 2 and inclusive. That becomes my domain of my function. If I look at this question here, and again, we're going to find the inverse and state the domain and range of the inverse. So we've got a function that is starting at equal to 0 and to infinity. When we're graphing for all real numbers, f of x is equal to x squared plus 1. So first thing we need to be thinking about, inverse will only occur if it's a one-to-one function. A quadratic is not a one-to-one function, but with a restriction at the turning point, it turns into a one-to-one function. Therefore, we can switch our x and y. So we've got y equals x squared plus 1. I'll switch it to x is equal to y squared plus 1, and then I'll make y the subject. So that means I will take 1 away, and then I'm square rooting. So I've got y equals the square root of x minus 1. As x and y switches, the domain of my function turns into the range of my inverse. Likewise, the range of my function turns into the domain of my inverse. So we already know our domain is 0 to infinity, so that will be my range of my inverse. Likewise, since this is my turning point, I can look at this and substitute 0 in, and I'm going to get 1. So this is going to give me a range of my function of 1 to infinity. So that returns into my domain. On the next question, we've got a function with a domain of real numbers. Sketch of real numbers of f of x is equal to x minus 3 bracket squared plus 2. Again, we're looking at inverse, and it only occurs if it's a 1-to-1 function. So this is a quadratic with no restrictions, which means it is not a 1-to-1 function because a horizontal line test shows it is that it is crossing 2 points. So therefore, it's not a 1-to-1 and there's no inverse. Whenever we are thinking about the inverse and we're wanting to find the points where f of x is equal to the inverse, the first thing we need to be thinking about is the mirror, is that intercepts will cross at y equals x. So this point here is where our inverse and our graph, our function will always cross. So using this, if I just put in my two functions to show, we can see that. I can see straight away that I'm going to have it crossing at -2, -2, and -1, -1. But if I don't have this graph just given to me, the best way for us to find where it's crossing is just using the function that's given and the y equals x and using simultaneous equations. So instead of saying y equals x plus 2 squared, I'll say x is equal to x plus 2 squared minus 2. I've just substituted x in for y. Now I can solve. X plus 2 squared is a perfect square, so that is x squared plus 4x plus 4. I can simplify by taking away x to get 3x, and 4 take away 2 is 2. Now I've got a quadratic, and this quadratic is monic, and it shows me that 1 times 2 is 2, and 1 plus 2 is 3, adding to b. So we know the relationship, it must times to equal AC and add up to equal B, and that's 1 and 2. Monic means that I can write it straight away. So that gives me x plus 2, x plus 1. So that gives me 2 points when x is equal to -1 and when x is equal to -2, which is what we can see right here.